Hi there, today we are going to talk about a topic which is beyond 5G as enabling technology for building smart ports or harbour cities. What exactly is B5G? B5G stands for Beyond Fifth Generation Networks, or so-called 6G, is the next generation of wireless communication system that will radically change how the society evolves. 5G technology has reached the transmission level with a peak rate of 10 gigabits per second and a low latency of 1 millisecond. B5G, or known as 6G, is integrating wireless communication with satellite communication to achieve the goal of seamless global coverage and interconnection. The application for frequency bands of B5G are in the range of 0.1 to 0.3 THz and 0.1 to 10 THz respectively. B5G will continue to improve XR performance, such as giving better mobility, shortened latency, and increased capacity to meet more XR services. XR stands for Extended Reality. Power consumption play an important role in B5G technology, as power consumption optimization of terminal devices has been widely discussed in the third generation partnership project, which is also known as 3GPP, and several technical standards has been formulated.
Now let's proceed to the features of Beyond 5G. The first feature is independent frequencies. The frequency range of 8 to 12 GHz is assigned to control channels for the 6G standard. It has a frequency bandwidth of up to 3.5 kHz and will have independent frequencies, which means the channels are not overlapping and allows different transmission to be given space, which helps increase data rates and provide better throughput. This enables much faster sampling rates than with 5G. The second feature is increased data rates transmission. Taking into the performance factor, 6G will contribute to higher performance, which is far better than newly deployed 5G wireless networks. Operating at terahertz frequency bands, 6G will deliver a peak data rate of 1000 gigabytes, having air latency less than 100 microseconds. When we talk about 5G versus 6G network speed, 6G speed is expected to be 100 times faster than 5G with enhanced reliability and wider network coverage. Following by the third feature is 6G wireless accelerates IoT after 5G. Internet of Things is becoming a reality today with the implementations of 5G-based solution following extensive 5G network testing, which was not possible with previous networks like 4G, LTE due to poor planning of frequency applied. Frequencies used were too narrow and crowded for transmitting data required by smart devices to give desired results. This is where 5G filled in the gap, and moving ahead with 6G, we expect to connect 10 times more devices per square kilometer, with increase in number of connected devices in the upcoming years. The last feature is low latency in both Gs. The time taken by a packet of information transmitted over a frequency is known as latency. 4G networks had a latency of about 50 milliseconds, whereas 5G networks had 10 times lower latency than 4G. With 6G internet, latency will slip down to range 1 millisecond to 1 microsecond, lowering latency to 5 times than the 5th generation network, making massive data transmission possible in less than a second. There are also multiple challenges to develop beyond 5G. The first challenge is artificial intelligence network. AI has been already applied in several areas such as AI images identification, voice identification, automated translation, and so on. For one thing, with the development of network services, higher requirements of network latency, reliability, users' experience are needed. Following by network security. By entering into 6G era, post-quantum cryptography as well as quantum key distribution and other technologies will be applied in network to ensure the absolute network security, and also the flexibility, redundancy, and self-healing capability. With the diverse applications of 5G or 6G in all industries, the technology is the solid basis of supporting digital manufacture, operation, and administration, which requires higher standard of network reliability and stability. For the implementation of Beyond 5G, the most important aspect of 6G technology is that it will bring better communication capabilities to the global community, which is needed in an era when the demand for digital engagement and data consumption continue to rise. With 6G, terahertz technology, which is a characteristic of 6G, will allow for even wider bandwidth, which means the possibility of receiving more data at faster rates. The implementation are significant and would mean increased consumption of data because the technology could withstand the rise in demand due to its very high data rate and very low latency. Many applications can make good use of 6G wireless networks. According to recent reports, 6G technology will support government and industry solutions in critical asset protection and public safety. Solutions will include facial recognition, health surveillance, and also threat detection.
Before we head into SmartPod, allow me to talk about the network architecture of 5G network. There are 4 layers in the 5G network model. Starting from the bottom is the open wireless architecture layer, which functions as a physical layer and data link layer of the OSI model. Next, we have the network layers that splits into upper and lower network layer, open transport protocol layer that acts as the transport and session layer in the OSI model, and last is the application layer that functions as a presentation and application layer in the OSI model. We will be focusing on the network layers, open transport protocol layer, and the application layer in this video. Let's start from the network layers. 5G devices have a separation of network layer into 2 sub-layers, which is a lower network layer for each interface and the upper network layer for the mobile terminal. These network layers are used to route data from source IP device to the destination IP device. The middleware between the upper and lower network layers shall maintain address translation from upper network address such as IPv6 to a different lower network IP address such as IPv4 and vice versa. Next, we have the open transport layer, which combines the functionality of both transport and session layer. Regarding the transport layer, the mobile and wireless networks differs from wired networks. This is because in all TCP versions, while it is assumed that lost segments are caused by network congestions, losses in wireless networks may occur due to a greater bit error ratio in a radio interface. Hence, for mobile and wireless networks, which solely use wireless links to retransmit missing or damaged TCP segments, TCP modifications and adaptation are suggested. Terminals for 5G devices will be much more suited to have a transport layer that can be downloaded and updated, and such devices shall have the option of downloading new transport protocol versions that are specific to a particular wireless technology installed at the base stations. Lastly, we have the application layer. This layer marks the data as per proper format required, does encryption and decryption of the data, and selects the best wireless connection for given service. Regarding the applications, the ultimate request from the 5G device terminal is to provide intelligent quality of service, QoS management over a variety of networks. The 5G device must allow for the storing of the measurement data in information databases within the device terminal, as well as the ability to test the service quality. The 5G device will store the QoS parameters such as delay, jitter, losses, bandwidth, and the reliability in a database to be used by smart algorithms running in the device terminal as system processes, which will ultimately deliver the best wireless connection under the required QoS and individual cost constraints. In order to handle a significant number of wirelessly equipped devices or the Internet of Things, IPv6 support for 5G and beyond is very crucial. By increasing the number of IP addresses, IPv6 eliminates the requirement for network address translation. Numerous creative coding schemes can be created for 5G devices and applications using the available address space and number of IPv6 addressing bits, which could aid in the development of the 5G network and services. Future wireless networks must include an effective method of negotiation between end users and the wireless infrastructure and low implementation complexity. Higher data rates and high-speed access for wireless devices are made possible by the Internet, and this will drive the evolution of an entirely device IP-based core network.
So we come to SmartPod, with 80% of the global trade handled by water and a 4% rise in worldwide seaborne trade, there is a growing interest in building a SmartPod ecosystem that uses information and communication technology, also known as ICT, to address port needs. Supply chain have experienced major modification in the context of Industry 4.0 and smart logistics. As a result, these developments are being accompanied by worldwide economic growth and progress. With that being said, this has necessitated a new configuration and supply chain architecture, as well as the rise of sustainability problems to coordinate the port's development. Smart port services and applications such as vessel and container management, technologies such as data centers, networking and communication, and automation. Use of sustainable technology to increase energy efficiency and reduce greenhouse gas emission. Cluster management such as a shipping cluster which consists of geographically proximate company and stakeholder whose primary activity is shipping. Development of hub infrastructure to support shipping. Increasing competition from ports worldwide. And lastly, terrorism and other security concerns. Next, onto B5G in smart port and harbour cities. To link Internet of Things devices or IoT devices to a 5G base station, these IoT devices must be 5G enabled. As a result of the resource constraint of IoT devices, we can employ 5G customer premises equipment, 5G-CPE. At the physical layer, data is evaluated and processed. The physical network is divided into three sections, for example, Enhanced Mobile Broadband (eMBB), Massive Machine Type Communications (MMTC), and Ultra Reliable Low Latency Communication (URLLC). So for the first section, which is Enhanced Mobile Broadband (eMBB), a fixed wireless access FWA, which will use 5G technology like beamforming and higher spectrum band to offer wireless internet to previously unreachable coverage regions, is one of the key ways 5G will be deployed across wide areas. FWA will have a huge influence on both emerging and developed global markets because sparsely populated rural area now lags significantly behind cities in internet connectivity. As 5G eMBB become more generally accessible, it will enable many sub-use cases including hotspots. For example, eMBB can improve broadband connectivity in highly populated regions by increasing interior and outdoor coverage in high-rise buildings and densely populated city centers. Broadband everywhere, technology such as FWA can provide consistent global coverage at minimum speed of 50 megabytes per second or Mbps. Public transit example include high-speed trains and various kinds of public transportation. Smart offices. eMBB can provide high bandwidth connection to hundreds of users in high traffic areas. Large-scale event, for example, eMBB may service concert and athletic events, allowing for high data rates when tens or hundreds of thousands of people are gathering. And lastly, enhanced multimedia. eMBB can deliver high-definition video, streaming, mobile TV, and real-time content over a wide region of service. Furthermore, onto the second section, which is Massive Machine Type Communication (MMTC). MMTC will connect tens of billions of IP-based devices over the 5G Mobile Communication System (MCS). 5G will be a fundamental component of smart ports, with 5G services and applications influencing smart network domotic, smart automobiles, and so on. The MMTC idea encompasses a collection of radio information and communication technology (ICT) and techniques, allowing for the predicted increase in number of terminal devices as well as related services and applications. There are three types of access technology: direct access, terminal device connect and communicate via direct access node, aggregation point access, and MMTC communication between devices. So the last section is Ultra Reliable Low Latency Communication (URLLC). Smart electricity grid and harbour automation are used to improve by using communication capabilities to provide better balancing of power. With the use of URLLC in 5G technology, it can provide a seamless and affordable communication platform for deploying advanced technology for managing power distribution network in a time of rising need for such flexibility and a growing amount of distributed energy resources. The Wireless for Verticals research project presented one of the real-life use cases of 5G relating to electricity grid and harbour automation. Low latency and high reliability are significant in this project to ensure the protection of electricity grid infrastructure and harbour automation. URLLC technology provides protection applications that allow 5G to have a reliable network connection with low latency, safety-related messages. This ensuring immediate clearance of severe faults to keep the electricity distribution network running. In the long run, users will benefit from increased safety of personnel equipment and reduced damage to that equipment.
Next, I will talk about the guidelines for 5G and beyond 5G. There are several guidelines for 5G and beyond 5G. For the first one is deployment. Development of the 5G network involves a variety of factors, including network planning, massive MIMO selections, coverage optimization, particularly in the uplink, time slot synchronization configuration, NSA and SA strategy, and network deployment stages. 100 Mbps downlink and 5 Mbps uplink are needed for the early 5G network deployment in order to provide the required level of service. Secondly, massive MIMO selection is one of the guidelines for 5G and beyond 5G. The use of massive MIMO in 5G is able to improve both coverage and capacity. There are three considerations of that need to be taken into account, which are performance requirements, installation requirements, and TCO saving. 5G network deployment needs to fully consider performance, cost, space, and weight limitation, etc. The most cost-effective configuration, 64T, 32T, or 60T, may be different for different deployment scenarios due to the different performance benefits in the scenarios, respectively. 64T or 32T tends to perform better in dense, urban, high-rise scenarios and hence may be more cost-efficient, where 32T or 16T tend to be more cost-efficient in urban and suburban scenarios. Thirdly, coverage enhancement. Downlink coverage is better than uplink coverage on C-band spectrum due to the large downlink transmit power of the G node B and disproportion in uplink and downlink time slot allocation of NR. Moreover, synchronization configuration. Synchronization of 5G network become the best way to avoid interference is to ensure the spectrum usage, does not require additional guard band, and reduce the cost of network equipment. Furthermore, NSA and SA strategy. SA is the target architecture, but the NSA ecosystem leads to SA for 6 months. The NSA can quickly deploy 5G network to support eMBB services and can be software upgraded to SA in the future. Last but not least, network deployment strategy in initial stage. The capacity of 5G network is larger than compared to the capacity of 4G network, which can gently enhance the user experience. In addition, operators need to consider 5G network deployment from high-value scenarios, which will focus on core urban areas, hotspots, and high-value areas to rapidly deploy 5G network and provide services with traffic and brand demand. High-value scenario and areas include CBD, university, government, hospital, airports, subway, venues, etc. High-value user include three types: user, high package, high traffic volume, and high-value terminal. Besides eMBB services such as video and VR, operators focus on industry incubation, evaluate the earliest mature areas including connected drones, industry internet, telemedicine, and so on, and work with innovative partners.
To sum it all up, Beyond 5G is currently the latest and greatest technology for wireless communication system, with a peak rate of 10 gigabits per second and a low latency of 1 millisecond compared to the first generation 1G with transfer speed of up to 2.4 kilobytes per second. Moreover, the features of Beyond 5G consist of higher frequencies that will enable much faster sampling rates compared to 5G. Independent frequencies, increased data rate transmission, 6G wireless accelerates Internet of Things after 5G, and provides a low latency in both Gs. Furthermore, Beyond 5G also have several challenges such as artificial intelligence network security, flexibility, redundancy, and self-healing capability. The use of next-generation computer networks, notably Beyond 5G, to the development of smart pods or harbour cities, IoT devices must be 5G enabled to a 5G base station. Because IoT devices have limited resources, we can use 5G customer premises equipment, which is known as 5G CPE, or fixed wireless access, which is known as FWA, which will leverage 5G technology such as beamforming and higher spectrum bands to provide wireless internet in smart pods or harbour cities. It's one of the primary ways for 5G will be spread across the large regions. Last but not least, there are several guidelines for 5G and beyond 5G such as deployment, massive MIMO selection, coverage enhancements, synchronization configuration, an SA and SA strategy, and network deployment strategy in initial stage. That's all from us. Thank you very much for listening to the end.